Hello Twitch. So welcome to our new meetup with Context Flow, where Julie and Michael are going to tell us how they're using deep learning and self-supervised learning for computer vision. Let me hand over to Julie. Just 1 second. Here we go. You're online.
Perfect. Well, hello, everyone. Thank you for having us. My name is Julie Sufana. I'm the Chief Marketing Officer with Context Flow. We're a Vienna-based startup developing radiology tools using artificial intelligence. And Michael Peeler is one of our deep learning and research and development engineers. So he's going to be doing the majority of the talking, but we thought it might be nice to give you guys an overview about our company in general. And if you're ever looking for a job, you know where to find us then. So I'm going to just share my screen. Let's see here. Perfect. So hopefully everyone's going to see my logo pretty soon. I think the internet connection, there we go. Good. So as I mentioned, Context Flow is based in Vienna, and we were founded in 2016 by 4 co-founders as a spin-off of the Medical University of Vienna, and we also received support from the Technical University. And actually, the original technology for what we do started as a European research project called CRESH-MOI back in 2010. So we've actually been developing the tools for a while. And the goal of this project was to develop a multilingual, multimodal search and retrieval system for medical documents. So at the time, we were only 4, and now we've very much expanded. So we're about 21 people. I think we're now from about 11 different countries and speaking just as many languages. So we're always looking for excited people to come and join us. And probably it's best, if you're not in the radiology domain, to give you an idea about the challenges that we face. So first off, as new technologies are emerging, so does the amount of data that's being generated. So it's very difficult for radiologists to know what data is relevant and to find that data right at the point of care. And this is really problematic because we're also facing a global radiologist shortage. And then on top of that, new treatments are actually requiring more complex diagnoses. So a radiologist may spend up to 20 minutes just searching for information to help them with a single case. And if you combine all those factors, it's like, well, you have fewer people doing more work that's more complex. And we know that that leads to a lot of delays and missed findings and really high overtime expense. So that's why at Context Flow, we've developed an AI backbone that's basically a group of products that are able to cover the radiologist's workflow from beginning to end. Everything that we do is designed to save them time, improve accuracy and efficiency. So I'll start with just our core technology, and then I'm going to turn it over to Michael so that he can talk about our R&D methods. Our core technology is a 3D image-based search engine. So if you can imagine a radiologist looking at images and coming across something that they don't immediately understand, the current process for them is to have to maybe guess a keyword. So they have to take whatever's in the picture and try and turn it into words, or maybe wait to talk to another radiologist. It's a really inefficient process. So we actually allow them to select a region of interest within, currently we work with lung CTs, and then we provide them thousands of other reference patients where they can compare and contrast. We can tell them the percentage of a lung volume that's affected by a disease pattern, as well as give them distribution heat maps to show where those patterns are located. And we also link them to reference literature that is really helpful for them when it comes to reporting, giving them differential diagnosis. So the goal is to try and put everything that they would need to solve a very difficult case in one place and really available to them instantly. The other thing that we do here that I'll briefly cover, triage. This is a tool that allows that radiologist to reorder their work list based on a specific or time-critical finding. So we calculate anomaly scores within the CTs, and then we can say, okay, patients above a certain threshold for that pattern, that's something that needs to get taken care of right away. Whereas right now, a radiologist really has no idea which patients in their work list have something that's really time critical. As I mentioned, we're always looking for curious individuals to join our team. Our website is contextflow.com. If you go to contextflow.com/jobs, that's where I always post our current listings. But even if you don't see an opening, we're always looking for deep learning, machine learning people. So you're welcome to send an email to jobs@contextflow.com. So that all is on the website. And with that, I'm going to turn it over to Michael so you can get into probably the more exciting technical aspects of what we do.
Thanks a lot. So let's switch to...
So yeah, hello everybody. Now I will start with my presentation. Can you see my slides now?
Works perfectly well.
Perfect. So today I will going to talk about self-supervised learning for computer vision. We will start with a short intro, then switch over to the SimCLR approach, MoCo, SwAV, and have a little bit of a look into future setups. And then there will be also time to discuss our setups and discuss the topic in more details. So yeah. So what's the fuss about self-super learning, and where is it different from supervised learning? So supervised learning is what we usually know as the traditional setup. We have our input data and we have the associated labels. This is like, for example, we have our famous dog and cat classifier, and we know each image is a dog or is a cat, and we can leverage that information for training. And what we try with self-supervised learning is, because we don't have the labels for our data, and usually have always much more unlabeled data than labels, you have to come up with a special learning objective that you can leverage the unlabeled data in a way so the model can learn kind of a structure of the data, or like a nice representation we can leverage later on. And this picture very nicely sums it up. On the left side, you have the supervised setup where the color indicates the labels. And on the right side, you have the same setup where you see we don't have the labels, but somehow the network has to derive some structure from the data, which can be leveraged later on. And in the usual setup, when you do unsupervised learning, later on, you switch to a supervised setup where you then can transfer the model, and it can make better use of the few labeled examples. And yeah. And before we dig into the methods in detail, I just want to show you a very nice slide, or actually two slides from Jan LeCun. And I guess they have a nice view on the topic, because here he compares it to a cake. And the cherry in this picture is like pure reinforcement learning. And if you don't know, it's not a problem. But in the end, what you do in reinforcement learning is you try to give the model like very few rewards, so just maybe a good or a bad, and the model has to do a lot in the background to get that reward, so the model only gets a few bits of information feed in where the model then knows where it stands and how it should adapt. And the supervised learning, he compares them to the icing of the cake, which is a little like the outside. And the self-supervised learning is then kind of the biscuit, so you can leverage a little bit more of the information content of the data. And then, and this is kind of also the structure what the model needs to learn. And what you will see later also when we look into the benchmarking of the different approaches is that usually also these models are a little bit, or need to be a little bit bigger than the supervised models in order to achieve them with retraining a similar approach. And I guess this fits then nicely to this view on this topic. And you will see that later also in the benchmarking curves. And yeah, we will focus on the self-supervised learning. And yeah, traditional self-supervised learning is usually set up in a way that you pretend that there is a part of the input you don't know and you want to predict that. And here you have the example with the future from the past, invisible parts from visible parts, and so on. So this can be that you occlude some parts of the image, cut it out, and the model has to predict that. This is like how this all started. And we will talk about contrastive setups and those SimCLR, MoCo, and SwAV. And there's a huge history and a very long history on self-supervised learning, and can highly recommend this paper down here if you want to know a little bit more, or maybe you have a special use case where there's maybe already stuff outside. And this is a huge blog post, but it's is a very nice thing to look up stuff and get a feeling what is out there. And yeah, I already mentioned those three methods we're going to talk about are contrastive methods. Then, of course, the question arises, what is contrastive and what's kind of the opposite, if there's like a real opposite. And usually there are two big groups for contrastive self-supervised learning. One is called generative or predictive setup. And in the end, one very famous example would be here the traditional autoencoder, where the data you feed in is also the data you predict. Or you feed in a grayscale image and want to predict the colors. And the important part is here, we measure here the loss in the output space. So the loss is really measured between the predicted pixels and the pixels of our ground truth. And this is in big contrast to contrastive setups. And this is also an important part, or a very important part, that we measure here the loss in the representation space. So we feed in here 2 data points that can be similar or dissimilar, and the model has to predict it here. And this is the setup we will focus on today. And this is from a recent review paper or survey paper about self-supervised learning. And they also put there like kind of this classification. And yeah, it's a little bit crowded figure, but I guess an interesting one. And you see here again, this axis is like we predict the representation, so not the input. So we're down here. And we kind of in between no labels and more labels. And you will see in a minute why we're kind of in the middle, because we predict our own labels in some way. Yeah, but now back to the setup. So how does the setup work? So usually we have our input image. And what we do in the first stage is we predict 2 different augmented views. And those views, we run them through our model, get some intermediate representation, and get a final representation. We will discuss these parts later on a little bit more in detail, and we do that also for other images. And the important part is here that we always use the same model. And in this prediction task for the loss, this is what you see here. It will be much clearer in a minute, but we always have here something which is like called a query, and a positive key and a negative key. If we take the image from the previous slide, we have here our image derived through 2 views. This could be our query, then this could be our positive key. So this relation is here that the positive key is like from the same image, and the other image can be our negative keys for comparison. And you will see why we need that in a second. Because when we compare those images, we do that with something called the info-noise contrasting estimation loss. And it sounds fancy, but in the end, it's a softmax loss. And you will see in a minute why. But before we dig into the formula itself, I just want to show you what we're trying to solve here, like on a very high level. In the end, we have here, we want to assign a score for our f from x. This can be our one view of our image, of our dog image, and this is the other view, like the positive example. We want to assign a very high score to those 2 samples. And if we compare our view from the dog image with the view from our chair image from before, we want to assign a very low score. So this is our task, or our contrastive task. So very high score for similar images based on the same image, and a very low score for images that are from a different base image. And this function is then captured in a softmax setup. And we want to like increase that, decrease the orange part. And in the end, our scoring function is a simple dot product. So if the two vectors are normalized and are the same, this will be converging to 1. And if they are dissimilar, this will then converge to -1 if the vector looks in the other direction. And yeah, so this is like the high-level setup. There's also a lot of theoretical background already out there where you see where this is more from like covered from an informational theoretical view. And yeah, this is also just that you have a point when you want to start digging a little bit deeper. So with that, with the basics covered, we can look into the SimCLR overview. And in the end, this is from the paper, and you will recognize here, this is what we have seen already before, our base image, our two transformed augmented views. Then we have our first network stage, which generates an intermediate representation, and we use the head output stage to generate our output representation. And here you see the stuff from before, but nicely animated, and I'll show you that because it's showing like what gets attracted and what gets repelled. So in the end, you attract the two views in the output space, so they should get similar, and you push away all other views from all other images. And this brings us also to the key findings. So in the SimCLR paper, they found out that you need a lot of data augmentations to make that work. And interestingly, much more than you would usually use in a supervised setup. And here you have a few examples. And interestingly, they have it, I guess, in the appendix that very strong color distortion was necessary because otherwise the model could learn kind of a shortcut because of the color composition. And I guess the idea behind it is, I don't know, so specific objects. I'm not sure if the dog is always like that, but it could be that most of the dogs are on an image with green grass in the background. And then the model learns maybe not the dog concept, but maybe just an object in front of a grass background. Yeah. And I guess this is a very interesting insight. And what they also did in their augmentation is that they contrasted global and local views, so bigger and smaller crops, that you get more details or the general part of the image, or most of it, and also crops which are next to each other. And this is what you have maybe asked yourself. I've also mentioned it before that we have this output head, this output stage. They found that if this multi-layer perceptron is nonlinear, that the representations or these intermediate representations are better and better separate the concepts there. And this is also an interesting insight. And another thing is that they normalize the embeddings with L2 normalization. And this normalization then embeds the vectors on a unit hypersphere. And we also look a little bit into that. What does it mean and why this is actually working and why it can be like a good thing. And here you have also the papers down here. You also see there's a version 1 and a version 2. So the version 1, so the version 2 is a little bit of a polished version 1, and we will also have that for the next paper, which you will then see in a minute. Yeah, and of course, something which is in this contrastive task very beneficial is the more examples you have to compare to, the better the training works. So you need very large batch sizes, which is also like maybe a drawback of this method, that you need a lot of GPU run to hold your data inside it. And here you see the results. Here up we have the supervised ImageNet Tab 1 accuracy. And here you have, with the red stars, the SimCLR results. And what you see here is with a similar sized model, it's the gap is bigger, and if you increase the model size for SimCLR, it's approaching the supervised setup, the accuracy there. And I guess one explanation for that is that this model pick up more structure in the data that is maybe necessary, but without supervision, they don't know what they need to pick up. So this can be also beneficial if you then want to employ your models for a wider range of tasks, I guess. And here you also see the MoCo setup, and this is the setup we have a look at after this setup. But before that, I'll just explain, features on the unit hypersphere. What is that? And why that is considered maybe beneficial in some cases. So when we L2 normalize our embeddings, this normalization then gets everything on the unit hypersphere. So you can because then every vector has a unit length of 1. All the embeddings point to points on this unit hypersphere. And it is thought that, or this is like not 100% like explored yet, but there are some papers who are pointing in the direction that this embedding on the unit hypersphere is helpful for a linear classifier to classify samples who are tied together in a specific region. So in this case, you see that in this part of this unit hypersphere, all the cats are very close together. So if we want to make a cat not cat classifier, the classifier would like kind of cut off this piece. And then if it's able to separate this piece of with the cats from the others, it would be able to classify the cats correctly from the others. And this is like the intuition behind it. Of course, we're not doing that in 2 or 3D, but in like, I don't know, 64D. But this is what this general setup is. And there was a very nice paper, which is also linked down here, where they dig a little bit deeper into this loss function, in the softmax loss function, and actually are able to attribute 2 modes of operation to the loss function. And this is the alignment and the uniformity. And I guess it's after, having heard that, it's kind of maybe an obvious thing, at least for the alignment. And in the end, the alignment means that if you put in similar images, like the airplane here, the same image, but just with different data augmentation, you want that the embeddings, the vector embeddings, lie very close together on this hypersphere, because in the end, they're very, it's in the end the same picture here, but just a little bit differently presented. So they should map to a very similar vector. But on the other hand, the loss function does something else, and this is kind of preserving uniformity, and this also means preserving maximal information. So so we want to attract the similar views, but want to push all other views away from our positive example, and this generates like an evenly separation of the other samples. And this has an interesting kind of feature, because that means we learn a lot about the structure of the data. And there's also like an interesting connection from this unit hypersphere, because usually when you so face re-identification system also use a similar system where they embed it on a unit hypersphere, and they even introduce like terms to make this decision boundary bigger. So there are like a couple of cosine-based losses, like ARA cos or something like that, or phase cos, I guess, or arc phase. If you're interested in that, I can send you also some starting points to dig into that. So this concept is also widely used for re-identification of faces or cars or whatever, because you can build very good classifiers that can map those input data to very distinct parts on this hypersphere. But now back to the high-level concepts for contrastive learning. And we have now seen SimCLR, and after the SimCLR version 1 paper, there was the MoCo version 1 paper. So you see there's also version 2 here. And the momentum contrast is very similar to the SimCLR. So this is why I would just show you here on the left side, this is the SimCLR approach. And the important part is here that the encoder here in the SimCLR approach is using like full back propagation. So we feed in our data, we get our loss, and then back propagate over all weights to update our encoder. However, the only problem with this setup is high batch sizes, and big models need then a lot of GPU RAM, and this can be problematic if you're not a very huge company which owns a big server farm. And this is where the momentum contrast option or setup can be very interesting. And what they do here is they decrease the batch size, use also the model like in a normal back propagation mode, but also have then here a model where they don't update the weights with back propagation, but with a momentum update. And the momentum update is very similar to what is happening at the momentum optimizer. So you take you have like here a factor M. You have your old weights, and you add on top 1 minus m of the new weights from the encoder. So this Q comes from the green model where we training it in full backpropagation mode. So you're kind of dragging the weights after each encoder update. The momentum encoder updates getting similar, but always a little bit lagging behind. But the idea behind that is if you generate here your output vectors, you keep them in a queue, and when you generate new ones, you always kick out the old ones. So you always have like kind of still up-to-date vectors that you can then use as negative examples in your loss function. So here, normal backpropagation mode. Here we update stepwise with the momentum update the weights, generate our embedding vectors. We use them for the contrastive loss. And here we always throw away the oldest one and replace them with the newest one. And this is like kind of, yeah, we try the momentum encoder network is kind of up to date to the encoder, because if we would not do that, of course, the embeddings we get out here are not comparable to those here if you would just update the network here. And yeah, with this trick, we get comparable results to SimCLR. But I guess the interesting part is not the image accuracy, because this is comparable, but you can maybe decrease your memory consumption and your training time. So this is an option when you have a smaller machine, I don't know, at work or at home. This is something I maybe would try first, because it should be easier to get it running and to get the results in a faster way. And yeah, so with that, I just want to explain another interesting concept from contrastive learning, or a thing when you think about a little bit closer that can be maybe a problem, and this is the number of false negative examples. And because we are doing self-supervised learning and cannot leverage labels, we can run into this problem here. So we have our image here, generate a positive, or we have compared here to the positive view or the positive example. And then we have here as a negative example, a cat in an airplane, that's working. But maybe we have the same kind of dog, but just another picture. And then, of course, we have a false negative sample. And that's and this paper linked here is showing that this addressing this problem can really boost your performance. And this is what they show here. So here we have the biased setup in green. I hope you can see the difference. And when you increase the negative sample size, so there the paper outlines that in much more detail, how you can like get hold on some parameters that you can tune your loss function, that you can avoid the impact of those negative samples. And the better you can estimate it, the better it will be. But you see, even just with a few negative sample size, you can increase your unbiased type 1 accuracy. Like it's like 6-7 percentage points. So it's something, yeah. And I guess it's a very interesting side note to this concept. So you see, if you can leverage your label information, or if you just have partly labeled data, this can maybe help. And just a side note, because it just came to my mind, the loss functions shown here, so where we're always contrasting views. There are also loss functions out there which do the same but leverage labels. So you try to group together images in the output space which where you know the label. So this is also something which you could maybe use. I mean, it was shown that it's a little bit better than softmax on its own, but I guess it always depends on your special setup. And if you want to do more with the embedding, that could be also very interesting. And with that,
So the question is, you would have to find out if your negative samples are, so your goal is to have a definition of true negative sample, right? So you don't have samples that are too near to the class that you want to classify. Yes.
You mean in this setup here?
Yeah. So this setup. So it's bad to have a dog, which looks similar, but and this is a dog, and this is a false negative sample, and this introduces some bias, right?
Yep.
And
I mean, in this case, I guess it will also depend. Or yeah, go on. Sorry.
So the idea is then to curate the data set and have a look for to find out what is the false negative samples, right? So you have got to import, you have got to invest time to create the data set which is unbiased.
I mean, this I guess is one option, but I guess that's one which is very time intensive or work intensive.
Okay.
They show they show that with a slight modification of the loss function, where you just take into account like one false negative sample, that you already can boost slightly your performance. And I guess before on a much higher level, I guess also the question is, what do you want to like achieve with your setup? Maybe you don't want to have a dog and cat classifier, but maybe you also want to have, I don't know, a classifier then in the end who wants to separate full dog shots to close-up dog pictures. Yeah. So I guess this will be also a little bit dependent on your future scenario. Because if you want to, I don't know, go for like super fine-grained similarity, maybe this is not a false negative anymore, because you want maybe looking for dogs in front of green plants, and here it's a dog on a earth floor. So I guess it will also depend on that.
Okay.
What is your downstream task then?
Okay.
But I guess this is still something, yeah. I mean, I have been thinking about, but I didn't come to a real conclusion, because I guess also this is not, or at least I'm not aware of publications that work or that show something in that direction, because it will likely, I mean, what they do here is top 1 accuracy is also again on ImageNet. So I don't know if you would do here, do that evaluation. Like, I don't know, you want to classify the background, if it's like earth or grass or just sky or whatever, yeah. I guess maybe this would look completely different, right? Then maybe that gap would shrink. So it's like a mixture. It depends on what you learn here, and also on what will you evaluate later then, and use your network for.
Okay, so biases.
But this is like a.
Okay.
Yeah, it's a tricky question, and I guess like at one point it gets very philosophical too. Yeah.
Okay.
But it's like, I guess that's interconnected, yeah. There's how you use it later. Mm-hmm.
So on the other side, semi-supervised settings like triplet loss, say hard negative mining is important. I guess that makes it hard to then also have low bias, right? So it's hard to get low bias in triplet loss.
In triplet loss, I mean, for triplet loss, you have to know the labels.
Yes.
So.
Or maybe we can discuss this afterwards in the Discord, so we
can
elaborate on that.
Yeah, okay. But it's a very, very good point. I mean, that in the end, the setup we are leveraging here, like comparing a lot of stuff with a lot of stuff, is in the end like a extended version of the triplet loss, right? In the triplet loss, we're using triplets. We have also this setup where we have like one anchor and a positive and a negative example. And in contrastive learning, what we do in the setups we have seen so far is that actually we try to increase the negative samples a lot to get better representations. Yeah, but we can also discuss it later. I guess it's a very interesting connection. Also because triplet mining has also some drawbacks, because you need to generate those triplets and easy hard triplets and stuff like that. But yeah, so we can definitely look into that later. But there are some big similarities. Yeah, I guess you can think of these loss functions I mentioned before, this contrastive loss where you use your labels. This can be considered like a multi-triplet loss, so to say, where you compare everyone with everyone and not just the triplets. Yeah. Maybe I can find the later the paper, and we can also use that in the discussion. But a very good input. Yeah. So yeah, and with that knowledge, we can go to the swapping assignments between views paper. And yeah, don't get discouraged. There is actually a lot in this figure going on, but we will start with the stuff we already know from the other 2 approaches. So we'll start again with our image, we generate two views. In this case, like an orange one and a green one. We use again our network, very similar setup like we have seen before, and we get our embeddings on the unit hypersphere. So those are the ones with the dashed line. And what we have in this SwAV approach is we do the comparison a little bit different. And I guess this is a very interesting concept. They use something called prototype vectors. So those vectors are randomly initialized and are trainable. And what we do then here is when we have our embeddings, so the embeddings, remember, are the dashed lines, we look for the next prototype vector and assign that view to this prototype vector. And in the next step, this is where the name comes from, we swap those assignments, and we have to, so for the embedding we get from the orange one, we predict, in the loss function we use as a prediction or as ground truth the green one, and for the green view we use the orange one, so we swap it. And we do that via soft assignment, so this is like, so we have a hard assignment and a soft assignment, and we'll leverage that in the loss function. And if you're interested in that, I can also give you some reading material. This is also a very interesting concept, which is like called optimal transport, if you want to look for that. But yeah, this is an own topic on its own. And here, now just to highlight the differences. So this is again our SimCLR MoCo setup. One image, two views, we run through our model, get the embedding features, and we compare them. And whereas with the SwAV approach, we do the same up until that point, and then we use the prototypes with this hard and soft assignment, and then compare them in this SwAV prediction task. Because in the end, the intuition behind that is, if we take these two views from the same image, this should map to the same prototype vector in the end. And this here now you see it animated. So again, we generate our views. We get our embedding vector, take the closest contrastive, or look where the closest prototype vector is, and then we swap that view and try to predict that. So this is really the high-level concept. The code is, and in the repo here down, is actually quite approachable. The only thing which I guess is maybe not so easy to get is this optimal transport problem. So you have kind of a soft assignment where you say how close, or when you have your embedding vector, the dashed one, you have the soft assignment is like a way to calculate how much, how close every vector from the prototype vectors is. But in the end, the SimCLR and MoCo approach are very similar, except this kind of comparison stage. And yeah, I guess in the paper they use kind of, I guess, 4,000 prototype vectors. So you have a lot of those prototype vectors. And maybe just a side note, because this always comes to my mind when I think about this concept, is I guess nobody looked yet what these prototype vectors learn. So I guess that would be also a very nice small experiment that when you train it on your data, maybe these prototype vectors are already related to some kind of label concepts. And maybe you can derive from those prototype vectors already kind of a meaning. I guess that would be an interesting thing to try, but I had no time yet to look into that. But this is something, yeah, which could be maybe, yeah, an interesting thing.
Another question.
And yeah, please.
So
yeah.
Two questions. Number one, how do you choose a good number of prototypes, and is the number of prototypes fixed beforehand?
Yeah, so the number is fixed. I guess it always, like the number is, so in the paper they try different numbers. As far as I remember, it's like they tried in the a few thousands and then just took what was fitting best. I guess it will depend on the kind of complexity of your data, because I could imagine, I don't know if you imagine a case where I just want to distinguish, I don't know, black from white images. Of course, this is like, yeah, a very simple case. Then maybe you would not need, maybe you would just need two prototype vectors if this is working at all, right? But I guess the more complex your data is, the more prototype vectors you maybe need. But I guess this is something, actually, I don't remember if but I guess they showed it also for other data sets. I'm not sure if they derive something in the paper now where they can relate the like the optimal number of prototype vectors to kind of the data set composition or setup. Yeah, but maybe we can look later in the discussion in the paper and yeah, find a hint there easily. I guess now we addressed both questions, right? It was like in one go. Perfect. And yeah, so and in the SwAV paper, this setup is one thing they changed to improve performance. So this kind of prototype assignment and swapped assignment. And on top of that, they also tried to improve the data augmentation setup, which was introduced in SimCLR and MoCo. And what they did here is, yeah, we have here like our input image, and they always produce just 2 or a couple of global views because they will take the majority of your GPU RAM, because those global views are, yeah, in the worst case, they have the entire resolution of your image data. And what they then do is they put in additional small views, so smaller crops of the data, and then compare them in the setup. So you have like 2 at least, or a couple of big views and much more smaller views. I guess they even use more than, I don't know, a couple of tenths, I guess. And this seems to be also beneficial, this setup, for the SimCLR and for the MoCo approach. If you just use that multi-crop data augmentation, you can also boost the performance there. And yeah, I guess the intuition behind it is that you want to your model to learn not just like the global view, but also like the details, and also how those details maybe relate to the whole picture. But again, I guess that will also depend very much on your data. And I don't know if there's actually does make a global view sense. I don't know if you take, I'm thinking of slices maybe of kind of tissue. Maybe this is not making sense if you use like a 5 gigapixel image, not just because it's very big, but yeah, I guess it will also depend on your use case all the time, how you would set that up. But it's like a very good hint on how you could set it up to boost your performance. And yeah, now to the results. So of course, it's now in shown as a third approach. So this is better than the 2 previous ones. And you see here in green, it's a supervised trained model that we're getting always a little bit closer here. Also with less parameters. So you see here, this is the MoCo version 2, SimCLR. So we're almost approaching the supervised ImageNet Type 1 accuracy. And yeah, here you see also the percentages. And here, the supervised benchmark they show in the paper is like 76%. And here we're like a little bit more than 1% apart, which I guess is very interesting. And yeah, especially if you have to work with data where you don't have a lot of labels, I guess this is really something to look into. Yeah, so after those 2 contrastive approaches, there was a very interesting paper about image transformers, and this goes more in like, you know, what could be possible future setups that could replace maybe those contrastive setups. And on a high level, like those transformer architectures were those kind of model architectures which were boosting the last couple of 1 or 2 years the performances in natural language processing systems by a lot. So this is what transformers are the base for all those BERT models for GPT-3, which you maybe have heard of in recent times because it's like one of the biggest models ever trained. And the idea was now, or the idea by OpenAI was, can this kind of transformer setup work for images too? Because in the end, that's a way also to learn the structure of your data and maybe use it again, leverage it again, like in a natural language processing setup for downstream tasks. And it turned out, yeah, this works. And yeah, this is how they did it. So in the end, they used images. So again, we have here a dog. But in order to cope with the kind of data, they had to downsample it. So this is the step here. We have our high resolution image, we downsample it, and then we put it in a vector. And this is what we used then for training. And to train it like you would train a language model. And one way to train a language model is like you predict the next pixel in a row of pixels, or for the language model, predict the next word after a row of words before. And or train it in a BERT way, which is like the mask language model approach, where you just mask out specific pixels and the model has to predict the other pixels. So here, this is predicting the next pixel. So you see it's a little bit shifted by one. And here you have to predict in the middle. So this is what was popularized with the BERT setup. And when they trained these models, they then evaluated like intermediate representation at the end of the model and used it for classification. And it turned out that this works. And it also comes with the interesting feature kind of feature that you know maybe from natural language processing, where you can feed in your network a sentence and the model finishes that. And this even works with this kind of models. And here you see some interesting results. On the left, you see what they feed the model. And here you see the completion. And I guess it's very interesting because all of those completions, I mean, they're also a little bit picked. So I guess here we have just the nicer ones. But you see, actually, the completions are not nonsense. So they like could all be possible things on how this image could be really be behind this cutout part. And I guess it's very interesting because with that, I guess one can say that the model learns kind of representation of data it has seen, and also knows that, I don't know, this slightly piece here of whitish rectangular stuff could be like a card or something like that. So I guess it's very interesting what the model picks here up. Or here the crossing, that we have something like crossings on the street, and this looks like a street, and in one case it even completes it like a crossing. So I guess this is a very interesting thing. The only drawback is, this is what you see now here, is we have to train on so this is a comparison. I guess here the last two lines are especially interesting. And this is called like IGPT, like image GPT model, that we have here. We have to use very small images because otherwise it's not doable. On the other hand, we have to use very big models. And you see here with the SimCLR approach, we can use much higher resolution sizes and need much less parameters and are slightly better. But I guess this is a very interesting future direction. And maybe just a final note on that. I guess this is like maybe the extreme form, because there have also been very interesting recent publications about self-attention networks, or SAN. And if you're interested in that, I can recommend this self-attention paper, because this is kind of something intermediate. Although with that setups, as far as I know, you're not able to like make this kind of completion feature work, because I would not know how. Maybe there's a way. They are more like trying to replace the convolutional operator with kind of attention-based mechanisms. But this could be kind of an intermediate thingy, but it's more closer to the CNNs we use nowadays.
So we have a question.
And please.
Just one. From before, so did they encode the pixel position into the vectors also?
I guess when they feed that in.
Otherwise, the multi-head attention loses structure.
Yeah, I guess. I mean, it's a little bit ago that I read the paper and the blog post linked here. I guess they used always this positional encoding, and that helped to the network to like kind of keep track of the location. But I would need to look it up. But usually this positional encoding is like a trick used in several setups where you want to encode position. And there was also recently published something called the visual transformer. And this is like taking this concept here, and more like maybe marrying it to computer vision. And they also use this positional encoding there. So this is why I would guess they do it here too. And because with that, I'm at the end of my presentation. So thank you very much for your attention. And now we can discuss details or how we use it, how we use contrastive learning. So I started using it recently at ContextFlow, but this is still like very early research. So I cannot really show some things or talk about that much because it's still training actually while I'm talking here. But I guess there's maybe a lot of further questions or stuff we can talk about. maybe also this triplet or this similarity to the triplet loss setup. But yeah, I guess we can now use the time for that.
Thank you for this very interesting presentation. So I give the audience like 2 minutes to head over to Discord, then we're going to close the stream. This is available right now also on YouTube, and everybody who's on the Meetup platform will get the link for the stream. I invite everyone to head over to Discord. Thanks a lot, Michael. See you later.
Also, thank you too. Yep, see you in a minute.
See you, bye.
So yeah, are there questions or points, or how did you like the presentation? I hope you enjoyed it and take a